In the previous video, we talked about pitch control and using stall, either active or passive stall, to control the aerodynamic torque. This figure shows the time history of the power output from a pitch-controlled 1 megawatt wind turbine located somewhere in Denmark. The wind speed is actually very high, right? It's close to 20 meters per second. It's close to the cutout speed already. It's so the wind speed is actually very high, and it fluctuates rapidly with time. So you can sort of see lots of high frequency content in the wind history curve. The horizontal axis is time in seconds. You can see it, right? So it goes from like 0 to 600 seconds, right? And lots of high frequency content in the wind speed history curve, right? So the wind speed actually varies very rapidly with time, right? This is a time history of the pitch angle, right? So how the pitch angle of the wind turbine actually changes with time. So this is a pitch controlled wind turbine, right? So you can change the pitch angle of the blades. So during the starting stage, so here there's no power output yet because the wind turbine is just starting. So at the starting point, the pitch angle is very high, 50 degrees or something, right? Very high pitch angle. So the very high pitch angle helps the wind turbine to start, right? Because the torque is larger at this kind of pitch angle, and then as the wind turbine actually starts to generate power output, the pitch angle is adjusted to smaller pitch angles, right? So starting from about 50 degrees and decrease it gradually to about 15 degrees or something, 10 or 15 degrees, this range, when the power output reaches the kind of rated power, right? But the time history of the pitch angle, first of all, it actually correlates with the wind speed history. So if you look at just the trend in the wind speed, the overall trend in the wind speed history curve, it actually correlates quite well with the pitch angle history curve, right? Second is that the pitch angle history curve is a lot smoother, right? It's a lot smoother than the wind speed history curve. It doesn't have this kind of high frequency content. It doesn't have these kind of very rapid fluctuations in it, right? The reason that the pitch angle curve is a lot smoother than wind velocity curve is that the speed for adjusting the pitch angle mechanically using that either an electrical motor or using hydraulic valves, the speed of adjusting pitch angle mechanically is actually a lot slower. It's a lot slower than the rapid fluctuations in the wind speed, right? So under turbulent wind conditions, it's actually a very demanding task to keep adjusting the pitch to the most appropriate angle under high loads. So a result is that the control system is very often caught out with the blades in the wrong position, right? Because the wind speed changes very rapidly, but the pitch angle adjustment process is kind of slow. So it is very often that the control system is caught out with the blades in the wrong position. It's not the most appropriate pitch angle for the wind speed at that moment, right? So the result is that we have very high fluctuations in the power output, right? We have excessive power variations in the power time history curve, right? And this kind of variation in the power output is actually very undesirable because the instantaneous power output can often exceed the rated power. If you look at the time history, it's actually quite often that the instantaneous power actually exceeds the rated power, right? So how do we actually solve this kind of problem? Associated with this kind of excessive power variations in output, right? There are various solutions, but the solution that's kind of probably the most famous was provided by a company called Vestas, and it's in their optislip system. They have a name for their system. It's called optislip, right? The idea is to actually dissipate the excessive mechanical shaft power through electrical means, which essentially requires a variable speed generator. So above the rated wind speed, so here this part of the graph is for above rated wind speed actually. So again we see strong fluctuations in the wind speed history curve. Right? Horizontal axis is again time, then vertical axis for this particular panel it's wind speed. Right? Very strong variations, very rapid variations in the wind speed. Right? And again, the variations in the pitch angle, right? The variations in the pitch angle is still a lot smoother. Than wind speed variations, right? And this particular panel, is for the generator rotor speed. It's the rotational speed of the generator rotor. It's not the wind turbine mechanical rotor. It's with the blades on it. It's a rotor inside the generator, right? It's the variational. It's actually the rotational speed of the generator rotor. Right? But we see very rapid variations in the rotational speed of the generator rotor. Right? It varies very, very rapidly. And you can sort of see some kind of correlations, right? You can see some correlations with the pitch angle. Right? But maybe there is a phase delay, phase shift. Right? It's an overall trend. But in addition to the overall trend, you see lots of high frequency variations in the generator rotor speed. Right? But if you look at the output power, if you look at the electrical power that comes out of the generator stator, it has almost no fluctuations. It's pretty much flat, right? Very, very flat. Very, very flat. Those excessive power variations that we see in the previous figure has disappeared, right? The fundamental idea behind the optislip system is to use an external resistor that is attached to the generator's rotor circuit to dissipate excess mechanical power from the shaft. So, in our previous discussions about the induction machine and the induction generator, right, we're pretty much just using the squirrel cage induction machine as an example. Right? For a squirrel cage induction machine, the rotor doesn't have an external circuit that's connected to it. The rotor is just like a standalone thing. It doesn't really have a extensive external circuit that's attached to it, right? But in the optislip system, the induction generator actually has a wound rotor, so which means that it has wires on it, right? And those wires can be connected to an external circuit, and through that external circuit, you can control the rotor and also the state of the generator. So now let's try to understand what exactly the optislip system is actually doing, right? But before that, let's find out what exactly will happen to the induction generator if the mechanical power from the shaft is too high. Right? Suppose the wind speed is very high and rotates the mechanical power is delivered to the generator rotor, so the generator rotor actually rotates very, very fast. So if it rotates too fast, what's going to happen, right? What's going to happen? So back in video 23, this is a slide I copied over from video 23. We talked about, in that video, we talked about the torque slip curve. The vertical axis is torque, horizontal axis is slip. It's called a torque slip curve of the induction machine. And we talked about stable region and unstable region on this graph, right? Stable region, that's the stable region. Slip goes from 0 to Sm, right? And the unstable region with the slip goes from Sm to like a very large value, right? For the generator mode, the slip is actually negative, right? So if you go along this axis, it becomes more and more negative, which means the absolute value of slip actually increases, but it's still negative, right? And then the torque is also negative, right, in the generator mode. because the generator actually acts as a back torque, it delivers a back torque to the mechanical torque, right? And the important thing is to realize that there is a stable region, and then there is an unstable region on this kind of graph, and we would like to make sure that the machine operates inside of the stable region, right? We don't want the machine to actually go over into the unstable region. So what exactly is the slip? Do we still remember what exactly is the slip? The slip is the synchronous speed subtracts the rotor speed and then divides the synchronous speed, right? So when the rotor speed is larger than the synchronous speed, the slip is negative, right? And then the induction machine is working in the generator mode, right? But the rotor speed cannot exceed the synchronous speed by too much, because if the slip becomes too negative, for example, it goes to the right hand of SM, right? If it becomes too negative, then the machine will enter this unstable region, right? That's what we do not want to happen, right? But how much is too much, right? How much is too much? For normal induction machine, the slip for the stable region is only a few percent, usually less than 3 to 5% actually, right? So SM is only about 3 or 5%, and usually it's actually less than that, right? Which means what? Which means the rotor speed cannot exceed the synchronous speed by too much. It cannot exceed the synchronous speed by more than 3 to 5%, right? In order for the machine to actually remain in the stable region. So in practice, this torque slip curve within the stable region is actually very, very steep. It's actually this particular graph shows you kind of the slope is not so steep, right? But in practice, the stable region has a very, very steep torque slip curve, right? So it's almost vertical. So which means what? Which means the normal induction generator is essentially a fixed speed generator, because the variation in the slip can only be less than a few percent, right? So it's pretty much has to work as a constant, a fixed speed generator, a constant speed generator, right? This is the approximate circuit of the induction machine that we derived in video 23, right? The total resistance on the rotor side, on the generator's rotor circuit, is just the summation of R2 prime and R2 prime multiplying this factor depending upon the slip. Right? If you add them together, it's R2 prime divided by S divided by slip. That's the total rotor side of resistance. Rotor side of resistance, right? In the generator mode, the slip is negative, right? So the total resistance is negative, which means it's actually generating power. Right? It's not dissipating. It's dissipating negative power, so it's generating power. Right? So as the rotor speed increases, if the rotor speed becomes very high, right, then the absolute value of the slip becomes very large, right? So R2 prime, that's sort of the copper, the apparent resistance in the wirings or in the copper of the rotor, right? And then divided by S. So if the absolute value of S actually increases, then it's on the denominator, right? So R2 prime is fixed. This thing only depends upon the hardware in the rotor. So this thing doesn't change. But if this thing actually has an absolute value that keeps increasing, then the division becomes, the absolute value of the division actually becomes smaller, right? If S keeps increasing, the absolute value of S keeps increasing, then the absolute value of this effective resistance actually keeps decreasing, right? And don't forget, the voltage is actually fixed at the grid of voltage, right? It's provided, this voltage is actually determined by the power grid. This thing doesn't change, right? So if this resistance becomes smaller and smaller, then the current that's flowing through this branch is going to become higher and higher. The amplitude, the absolute value of the current is going to increase as the slip increases. as the absolute value of slip increases, right? So if the rotor speed is too high, and then the absolute value of this resistance becomes too low, and then this current becomes too high. If this current becomes too high, then it may burn the generator, right? So the solution provided by the Vestas optislip system is basically to connect another external variable resistance to the rotor side of the circuit. So if we denote this variable resistance, external variable resistance, as Rx divided by S, the slip, as the absolute value of the slip increases, as the rotors rotates faster and faster, this external resistance Rx can be increased proportionally, such that the total rotor side of resistance, the total rotor side of resistance is not R2 prime divided by S anymore. It's R2 prime plus Rx divided by S if you connect this external resistor to the rotor, right? So as S increases, as the absolute value of S increases, what we can do is to increase this external resistance Rx such that in a way such that Rx plus R2 prime divided by S keeps constant. So the Rx plus R2 prime divided by S is now the total rotor side of resistance, counting for this taking into account this external variable resistance that's added to the rotor, right? So Rx can be varied in such a way so that the absolute value of this particular rotor side of a total resistance keeps constant, right? So if Rx can be varied automatically in such a way, right, then the current will remain constant because the resistance is constant. So the current is not gonna change, right? Because the voltage is not gonna change. So there is no danger of burning the generator, even at very high rotor speed, right? If the rotor speed is very high, we just make Rx high enough so that this ratio keeps constant, right? So in this case, we can actually keep the current, the amplitude or absolute value of the current within the bound, within a fixed bound, right? So there is no danger to burn the generator. And what about the stable and unstable region, right? What about that? If we look at the torque slip curve again, what exactly is the result of increasing the rotor side of external resistance, right? What's actually the result of how we are going to change the torque slip curve if we increase the rotor side of external resistance? In video 23, we plotted this torque slip curve for different values of R2 prime. Here R2 prime is what? R2 prime is the stator side apparent resistance of the rotor, right? It's basically mapping the rotor side resistance to the stator side. So that's why we have a prime here. We're treating the induction machine as a transformer, right? So we can actually map the secondary circuit to the primary circuit, and R2 prime is the resistance of the rotor, the secondary side of circuit mapped to the primary side, to the stator side, right? So if we increase R2 prime, the torque slip curve is going to change, right? But how it's going to change, right? The peak torque, the maximum torque, the level, the amplitude of the maximum torque is going to stay constant. It's not going to vary. But the entire curve, the location of the peak, is going to shift to the right, right? So the blue curve is for the smallest R2 prime, and this cyan curve is for the largest R2 prime, right? You can sort of see the maximum torque is about the same, right? But the location of the peak has shifted from like a 0.1 to like a 0.75 or something, right? So as R2 prime increases, the peak of the torque slip curve shifts towards the right. What's the effect of connecting an external resistance Rx to the rotor side, right? What's actually the effect? The effect of connecting an external resistance Rx is actually equivalent to increasing R2 prime, basically, right? It's an equivalent effect. It's an equivalent effect. So as we actually increase the external resistance Rx, we are basically just shifting the torque slip curve to the right, right? And as we actually increase Rx, as the curve actually shifts to the right, the stable region, the range of the stable region also increases. The stable region is from zero slip to the peak, to location of the peak, right? So as the curve shifts to the right, the stable region also extends, right? If the stable region extends, the machine is going to allow the slip and also the rotor speed to vary within a wider zone, right? So by connecting an external resistor, it actually solved both problems. It has extended the stable region, and then it provided means for controlling the current so that the generator won't burn, right? So how do we actually connect the rotor to an external circuit, right? We will actually need a wound-rotor induction machine, which is also called the slip ring induction machine sometimes. So back in video 25, we mentioned there are two different kinds of induction machines, right? The squirrel cage induction machine that uses a squirrel cage rotor, which essentially has no wiring on the rotor side, right? And then we also have a wound-rotor induction machine, which has extensive wiring on the rotor, right? So the stator on both kinds of induction machine are pretty much the same. There's almost no difference. The major differences are just on the rotor. So the rotor in a squirrel cage induction machine does not have windings on it, right? But the rotor in a wound rotor or slip ring induction machine actually has three-phase windings with a number of poles that's kind of identical to that in the stator, right? So you can put wirings on the rotor in a way that's kind of compatible with the wirings in the stator, right? And then the end point of the winding for each of the phase is then connected to something that's called a slip ring. So you have three phases, right? And each of the phase has its own winding. And then the end of the winding for each phase is connected to one separate slip ring, which is normally just a copper band molded onto an insulating material and then pressed on the steel shaft of the rotor, right? So on this diagram, you have like three wirings in the rotor. So this is the rotor. This is the rotor. This smaller circle represents the rotor, and then the larger circle represents the stator. You have windings in the stator. That's expected, right? But now for the wound rotor induction machine, also have wirings on the rotor, and those wirings for each phase it's connected to a slip ring, right? On this diagram, it's just represented as a black dot, but in reality, those black dots actually correspond to those slip rings. Right? So as the rotor rotates, so these are the slip rings now. So this is a close-up picture of the slip rings. So as the rotor rotates, the slip rings also rotates with the shaft. So how do we actually connect those rotor windings with the stationary external circuit, right? How do we actually do that mechanically? the solution is to use a stationary brush. So there are stationary brushes. Those are the brushes. So there are stationary brushes that's pressed against the slip rings. So as the shaft rotates, the slip ring rotates, right? But the brushes are stationary. The brushes are not moving, and because they are pressed against the slip rings, right? So they are actually constantly in contact with the end of the wirings that's kind of connected to the slip ring, right? So usually those brushes are made of a combination of copper and carbon. So through the slip ring, through the slip ring, each brush is actually connected with the end of a winding on the rotor, right? Because you have like three slip rings, you have three slip rings, right? And then you have three brushes, three stationary brushes, right? Each of them is actually in contact with one of those slip rings, right? So those stationary brushes are then connected to an external stationary circuit, right? So the external circuit doesn't have to rotate together with the rotor, right? So if the external circuits are not needed, if we don't want to connect with the external circuit to the rotor, right? Those slip rings can be short-circuited by using a metal collar, right? That metal collar is going to connect those slip rings together, and the brushes, or those brushes, those brushes can be automatically lifted from the slip rings to avoid any kind of friction, wear, and tear, right? If you lift the brushes, it's going to lose contact with the slip rings. And in this case, the wound-rotor induction machine acts pretty much the same as a squirrel cage induction machine, because you don't really have an external circuit connected to the rotor, right? So if the wind turbine uses a wound-rotor induction generator, what might be the external circuit that can be connected to the rotor, right? In the Vestas optislip system, it is a variable external resistor that is connected to the rotor circuit. The excess mechanical power delivered to the generator's rotor, which is also known as the slip power sometimes, right? The slip power is pretty much just dissipated as heat on the resistor and serves no useful purpose. So the optislip system allows for very high slip operation. So the rotor speed can be very high, can fluctuate very quickly, right? It allows for high slip operation of the induction generator, but it does not allow recovering the excess slip power to a useful form. So for slip power recovery purposes, we will need to replace that external resistor with something that's called a power converter. We have not talked about power converters yet. But the purpose of this power converter is to convert the AC power that's coming off the rotor of the induction generator into a form that can be connected to the utility grid. You can sort of see, you have in this particular diagram, you have the induction machine here, right? The outer circle represents the stator, right? You have three-phase wiring that's coming out of the stator, and that three-phase wiring coming out of the stator is going to be connected with a transformer, and then it's going to be eventually connected to the utility grid, right? This part of the circuit also exists in the ordinary squirrel cage induction machine, right? If you are using just an ordinary squirrel cage induction machine, that's pretty much the wiring that you are going to get, right? So all the power is coming out of the stator. But if you are using wounded rotor, now you have three-phase wiring. You have three-phase wiring that's coming out of the rotor now, right? So those lines are connected to the rotor. So that's sort of the rotor part of the induction machine. That's the smaller circle inside of it, right? And this rotor is connected to a gearbox, which is eventually connected to the wind turbine rotor, right? So wind comes this way, right? Right. That's this part of the wiring. This part of the wiring is provided only by wound-rotor induction machine. For squirrel cage, you don't have these kind of 3 wires that's coming out of the rotor. But now by using a wound-rotor induction machine, you have these wires that's coming out of the rotor now, right? But the problem with the AC power that's coming off the rotor is that it is actually at a different frequency from the frequency of the utility grid. And back in video 22, we actually talked about the frequencies, right? We derived that the frequency inside of the rotor actually equals to the frequency inside the stator multiplying the slip, right? The frequency inside the stator is the same as the frequency of the utility grid. It's 60 Hertz in the US and 50 Hertz everywhere else in the world, right? But the slip is usually not unity, right? It's not 1. It's actually very far from 1, actually. So the frequency inside of the rotor is actually very different from the utility grid frequency, right? So the purpose of the power converter is to first, it will rectify the AC power from the rotor into the direct current or DC power. So it's going to convert the AC power coming off the rotor, which is at a very different frequency from the grid frequency, right? And then it's going to convert that AC power into DC power, right? Now you see just the 2 wiring coming out of this block, right? One is positive, the other one is negative. It's just like a battery. Battery has just two terminals, right? The DC power coming out of this block has just 2 wires, right? And then this block basically just converts the DC power that's coming off this block into the AC power with the correct frequency, with the grid frequency, right? Which is 60 Hertz in the US and 50 Hertz everywhere else, right? And you may have to use a low-pass filter to actually sort of regulate the power better, into a better shape, right? And then you give it to the transformer, right? And then the transformer actually gives it to the utility grid, right? So the whole thing, this part of the circuit, is missing in ordinary squirrel cage induction machine or fixed speed wind turbine, right? But now by using a wound-rotor induction machine, you can actually add this particular external circuit to the rotor. So if you actually treat the power converter as a whole, from the rotor side, if you just look at the entire load on these 3 wires on this particular on this side of the terminal, right? The power converter actually appears as an external resistor. So the voltage across this port, across these terminals, and the current across these terminals are going to be, the phase of them are going to be different by like 180 degrees, just the minus sign, right? Because the power is actually flowing out, right? Otherwise, it's going to be sort of a yin phase if you do not account this kind of a change in psi, right? So it's going to appear as an external resistor to the rotor, right? But instead of dissipating power as heat, this particular external circuit is going to capture the excess power from the rotor and then convert it into electricity that can be pushed to the utility grid, right? So the entire circuit will still have all the benefits of an external circuit. It's going to allow for a wide range of slip and also rotor speed, right? And then it also will keep the current in the generator constant right? So the generator will not go over the rated power, rated current, so it's not going to burn, right? There's no danger of burning, right? So all the benefit of using an external resistor is kept, right? But in addition to that, those excessive power, excessive slip power that's delivered to the node, to the rotor of the generator, are going to be converted into useful electricity that's going to be pushed to the utility grid, right? This kind of a wound-rotor induction machine is also known as the doubly-fed induction machine, DFIG, or double output induction generator. Right? It is certainly more expensive than the squirrel cage induction machine, but it is still quite economical. It's still quite affordable, especially for those utility-scale large wind turbines. In fact, this kind of a configuration is becoming more and more popular in modern variable speed wind turbines.